Hey, Chem 2, hope everybody's doing well. This is Dr. Ricardo. We are going to be doing the fifth of six videos for chapter 16. Okay, so we left off on page 15 of the notes. We finished talking about acid-base indicators. So the next section, we're going to do some problems related to calculating the pH of a solution that has either an acid or a base in it. So I'm going to show you how to do that. So there's going to be some problems where you have a strong acid or a strong base that's dissolved in solution and you want to calculate the pH, and some problems where we have a weak acid or a weak base and you want to calculate the pH. Okay, so let's take the first example. Again, middle of page 15. A solution of barium hydroxide at 25 degrees is 0.125 molar in barium hydroxide. What is the pH and hydronium ion concentration of this solution? All right, so the first thing that we should do is we should write down the equilibrium, okay, or in this case, the chemical reaction. Now, if you remember, barium is one of six different strong bases that you should have memorized. Anytime you have a metal from group 1 or group 2 of the periodic table, that's either of lithium, sodium, potassium, calcium, strontium, or barium, any of those hydroxides, they're going to be strong bases. That means they completely dissolve in solution. And then they create a quantitative or a stoichiometric amount of hydroxide related to the original quantity of barium or whatever the metal is that was delivering them. Okay, so the chemical reaction is barium hydroxide solid dissolves in water to make barium plus 2 and 2 hydroxide ions. Okay, so this coefficient of 2 comes from this subscript of 2. Barium is in the second group of the periodic table, so barium hydroxide is not going to be BaOH, it's going to be Ba parentheses OH2. Okay, now we don't have an equilibrium here because we have a strong base. So we're just going to leave out the equilibrium step. So instead of doing an ice table of initial change in equilibrium, we're just going to do a before and after table. Okay, so before this starts to dissolve, I have 0.125 moles per liter of barium hydroxide. Okay, and before it starts to react, I have 0 of this and 0 of this, so it has to go to the right. Since this is a strong base, it's going to go completely to the right. I'm going to use up every last bit of the barium hydroxide. So after the chemical reaction is done, this guy's going to go down to 0. Okay. If I started with 0 barium dissolved, and for every 0.125 moles per liter of barium hydroxide that dissolves, I get the same exact amount of barium. Why? Because this is a 1-to-1 relationship. Okay, but I get twice as many barium hydroxides. I start with 0, right? Because water essentially has 10 to the minus 7th moles per liter of hydroxide. That's such a small number that you can consider it 0. Okay. So this guy is double compared to this. Why? Because of that 2 and that 2 over there. Everybody see that? For every one of these that goes into solution, I get twice as much hydroxide. All right, well, if that's the case, I know that my hydroxide ion concentration at equilibrium, because there is no equilibrium, it goes all the way to the right, is 0.250. So the first thing to calculate is pOH. Okay, so if you know the OH minus concentration is 0.250, then how do you calculate the pOH? So the pOH is minus the log of the OH minus concentration. So I turn my calculator on. Let's see if I can do that, right? And then I'm going to say I want the log. Let's see how this calculator works if I could put it in first. I want the, not second function. I think I'm going to try this calculator. I'm going to put the number in first, and then I will take the log of it. So 0.250, and then I take the log of that number, Okay, gives me that number. So the log of 0.250 is 0.602. Okay, so that's the answer that comes out. But look, this has a minus sign in front of it. So anytime these guys are fractions, the log of a fraction, a log of a decimal number or a fraction is going to be a negative number. So that negative is going to cancel with that negative. So negative the log of 0.250 is going to give you a POH of 6, right? Because the log of it's going to come out to negative, and again, a negative, negative, it's going to be a positive. Okay, why can I lose that 2? Because this guy had 3 significant digits, so this guy has 3 significant digits. Okay, so 0.6 is fine. Okay, well, if the POH is 0.6, we know from this formula that pH plus POH is always equal to 14, so the pH must be 14 minus 0.6, which is 13.4. In any aqueous solution, the pH, 13.4, plus the POH, 0.6, has to equal to 14. And the last step, okay, there's multiple ways to do this, but the way I chose to do it here is what's the hydronium ion concentration? We got the first part of the answer, 13.4 is the answer to the pH, right? They wanted to know the pH of the solution. The hydronium ion concentration then is going to be take the antilog of minus the pH. Some people look at it like this. They say the hydronium ion concentration is equal to 10 to the minus whatever the pH is. Okay, so the hydronium ion concentration is going to be 10 to the minus 13.4. Okay, so how could I do that on my calculator? I can do it this way. I can put in 13.4, put a negative sign in. So I put 13.4 negative, I'll show you that, 13.4, and plus or minus, I put a negative sign in front. So I use this key here. And then the last step, I need to take second function log, because second function log is 10 to the x of that number. So log would be just to press the button now. If I hit second function and then log, it's going to do what's up here in gold. So second function log. Okay, so I get that the hydronium ion concentration, this sort of makes sense, is going to be equal to 3.98 times 10 to the minus 14th. And that's what I got here, and that's what I got here. So try that yourself. Don't believe me. Please do it on your calculator yourself. Okay, so that's the answer to the first question. Okay, page 16 is going to give more examples. So let's take a look at the next one. Okay, that was pretty easy because it was a strong base, so I didn't have to do an ice table. Okay, this one's easy too. So you have to remember that the pH meter is live, right? It's like it's not a snapshot. It's like a movie. It's constantly giving you whatever the hydrogen ion concentration is. Okay, so the pH meter is giving you an equilibrium value. Once it stops going up or down and settles at one place, that's the equilibrium concentration of hydronium ions in solution. So here's the question. The pH of normal arterial blood is 7.40. What is the hydrogen concentration of this blood? Well, this is easy. Remember, the pH, if you know the pH, you can automatically calculate the hydrogen ion concentration. So here's the definition. pH is equal to minus the log of hydronium ion concentration. The problem is we have this number over here. We're going to put a 7.4 in there. Okay, so two ways of looking at it. The hydronium ion concentration is the anti-log of negative 7.40. The other way of looking at it is the hydronium ion concentration is 10 to the minus whatever pH is. And in this example, we're going to plug a 7.40 in there. So either way, okay? So 10 to the minus 7.4 or the antilog of 7.4. When you do that, you get 3.98 times 10 to the minus 8. So practice these yourselves, guys, and make sure you get it right. So I'm going to try it now on this simple calculator. Okay, I need 7.40 with a negative sign, right? So I do it again, 7.40, change the sign to negative. Then I hit second function, right? See the little second function button come up here, and I hit LOG. Okay, now that gives me a little teeny tiny number, which I could count back to get to 10 to the minus eighth, right? I could count back. But most of these calculators have a button someplace that goes between the floating point number and the exponential form of the number. So right now it's in a floating point number. If I hit this F to E button, it should put it into scientific notation. Okay, so that's the exponential form. So 3.98 times 10 to the minus 8. They don't write that this part, the important part, the times 10 to the minus 8th, you've got to assume that there's a little times 10 to the minus 8th in there. Okay, so that's what that means, right? Don't write all this extra stuff down, way too many significant digits. This means that, okay? Okay, next example. Well, let's talk about aqueous solutions of weak acids and weak bases. So we're going to call the equilibrium constant for a weak acid the Ka. So the Ka, remember, since it's an equilibrium constant, is a capital Ka. Small k is for a rate constants, capital K is for equilibrium constants. And we're going to call the equilibrium constant for a weak base, the reaction of a base with water to make hydronium and the counterion Kb. So let's start with the Kas. So Ka is defined as the acid dissociation constant. It's the equilibrium constant for the ionization of a weak acid. In general terms, and they're all going to fit into this, in general terms, I have my acid HA, right? It's got an extra proton that it's ready to donate. It could even have a charge on here. It's still HA. It reacts with water, donates a proton to water because it's the acid, okay? Typical Bronsted fashion, donates a proton to water. Here comes the proton, making hydronium ion and the counter ion. The counter ion is what's left over after HA dissociates. So if the H comes off and goes to water, what's left? A minus. Okay, so if this was HF, then this would be F minus over here. So all equilibrium constants, including Kas, you take the concentration of the products divided by the concentration of the reactants. The coefficients become the exponents. So I get a hydronium ion to the first power, A minus to the first power, HA in the denominator of the first power, and I leave off the liquid water, right? There would be a bracket water down here, but we said the convention is we always leave off liquid water because it doesn't change very much. Okay, you'd just be dragging an extra 55 down here. It's always going to be around 55 moles of water in water. Okay, another definition, something called the degree of ionization. It's kind of a measure of how far the reaction took place. Okay, so the degree of ionization is the fraction of molecules that dissociate into ions. In the case of any weak acid, the degree of ionization is the equilibrium concentration of A minus, right? Because as the AHA dissociates, I always get a certain amount of A minus with respect to it, no matter what's going on. How much of this I have at equilibrium divided by the amount of HA that I start with. So it's the equilibrium concentration of A minus divided by the initial concentration of HA that I started with. So usually you're going to know this. You're going to be given this. You can calculate this, and then the degree of ionization is just that relationship, that fraction. This is always going to be a number that's less than 1, right? 1 would be 100% dissociation. So if I had a strong acid, 100% of the HA would go over here to A minus, and I wouldn't have anything left over here. So this guy over here and this guy over here would be exactly the same, right? I'd get exactly the same amount of A minus as the HA that I started with. So let's say this was, I started with a 0.15 molar solution of HA, and it was a strong acid and completely dissociated. Then I'd get the same exact amount of A minus. So this would be a 0.15 up here divided by 0.15, and I'd get 1. So 100% ionization is a degree of ionization of 1. 0% ionization would be that nothing happened, right? That this reaction was terrible and it didn't happen at all, or that the back reaction was so much more favored than the front reaction. Well, if that was the case and nothing happened, then this numerator, A minus, would be 0. My amount of HA would still be 0.15, and I'd get 0 divided by 0.15, and 0 divided by anything is going to be 0. So this is bound, this degree of ionization, between 1 and 0. The highest value it could be is 1. The lowest value is 0. 1 meaning 100%, 0 meaning 0%. Good. Okay, let's do some more problems. This is the top of page 17. Determining the Ka from solution pH. Okay, so in this example, I'm going to give you some experimental data, and you're going to back calculate what the Ka must have been based on this reaction. So let's read it. Nicotinic acid, which is the acid that makes niacin, is a monoprotic acid with the formula HC6H4NO2. A solution that is 0.0120 molar in nicotinic acid has a pH of 3.93 at 25 degrees C. What is the acid dissociation constant? Okay, so we're going to try to calculate the acid dissociation constant. Ka for this acid at 25 degrees. What is the degree of ionization of this acid? Okay, so first thing that you want to do is, if they give you the pH, you can calculate the equilibrium concentration of hydronium ion concentration, right? And we said that to do that, you need to put a negative sign on pH and take the antilog, or equivalently, go back to this guy over here, right? The hydronium ion concentration is equal to 10 to the minus pH. And in this case, it's the number that we're going to plug in there is 3.39. So 10 to the minus 3.39 is equal to what? Okay, so I'll do that one for you. You try it at home. Okay, so if my pH is 3.39, slap a negative sign on. 3.39, put the negative sign in. Right, change the sign to negative, hit second function log, and I get the antilog. Okay, going to get 0.00407. We want to change that to scientific notation. Hit that button. I get 4.07 times 10 to the minus 4. So I had rounded it up here, which is fine. 4.07 is rounds up to 4.1 times 10 to the minus 4. Okay, so that means after this niacin is added to water, the hydronium ion concentration goes to 4.1 times 10 to the minus 4th. That's the equilibrium amount. Okay, let's write out the equilibrium constant chemical reaction, and then the ice table, and then plug in. Okay, so how much HA did I have initially, right? I is for the initial quantity. Well, that's 0.0120. So that number comes right down here. How much H3O plus do I start with? None, right? Remember, in aqueous solution without anything else in it is 10 to the minus 7th. That's basically none. Do I have any A minus? No, I don't have any of the counter ion from niacin yet because it didn't react. So I have zeros over here. Okay, anytime I have an equilibrium and I don't have anything on one side, we know the chemical reaction has to proceed or get out of the gate by going from left to right because I have to fill in these zeros. Something has to occur. Zero can't react with zero to make this because you don't have any stuff there. Good. All right, so let's talk about for every, oh, next thing that we know. I know the hydronium ion concentration at equilibrium is 4.1 times 10 to the minus fourth. So this came from up here. I know that because the pH meter gives me the equilibrium concentration. Okay, well, how did I get 4.1 times 10 to the minus 4 from 0? Well, the only way to get from 0 to 4.1 times 10 to the minus 4 is to add 4.1 times 10 to the minus 4. So we know this one from the pH. pH gives you an equilibrium concentration. We know we didn't have any to start with, or an insignificant amount to start with. So 0 plus what number gives you 4.1 times 10 to the minus fourth? This has to be plus 4.1 times 10 to the minus fourth. Remember, changes are going to always be positive for products and negative for reactants. So I can fill in this whole column first. Okay. All right. Now we do the stoichiometry. Okay. Let's pretend that these two numbers, nothing was filled in over here. Okay. Well, if this guy started out at 0, went up to 4.1 times 10 to the minus fourth, it's definitely a true statement that for every one of these that formed, one of these also had to form, right? Because it's one-to-one stoichiometry. So this is going to go up by that number. This is going to go up by that same exact number. How much do I have at equilibrium? Well, if I start at 0 and I go up by 4.1 times 10 to the minus 4, 0 plus 4.1 times 10 to the minus 4 equals 4.1 times 10 to the minus 4th. Okay, what's happening on the right-hand side, excuse me, on the left-hand side? Well, here's my initial concentration that they gave me from the question, right here. Okay, for every one of these that was formed, one of these must have reacted, right? This is a one-to-one chemistry. So this goes down by that number. Excuse me, this goes up by that number. This goes down by that same exact number. Okay, how do I get the equilibrium concentration of HA or the niacin? I take what I started with, I subtract off how much reacted, and this is what I have after it reacted. All right, so these three numbers, guys, down here, boom, boom, and boom, are equilibrium concentrations. I can plug them into Ka. Okay, so the Ka, I didn't write it, but the Ka is the products divided by the reactants, coefficients become the exponents, and leave water out. So this times this is the numerator, divided by this. So take this column down here. Well, look, this times this, they're the same exact number. So I put that number in and square it. Okay. Divided by the concentration of 0.116. Okay, I think I'll try to write in here. I'll write this in here to help. This is going to be H3O plus, A minus, all divided by HA. So this times this, put that number in, a number times itself is the number squared. So that's where that came from. And this is that number over here. Good. All right, that didn't come out so neat, so I'll just erase it for now. Okay, do the math. Take the numerator, square it, divide it by 0.0116, and I get 1.45 times 10 to the minus fifth. So that's the answer. The question was asking for the equilibrium constant. You calculated the equilibrium constant. The second part was they wanted you to calculate the degree of ionization. So the degree of ionization is how much A minus you have at equilibrium, right? Provided that it only came from the HA to start with. You didn't have any initial amount of this, which you didn't. divided by the starting amount. So it's kind of the part over the total times 100. Okay, so the degree of ionization was 3.42. That means for every 100 molecules of HA that I start with and I put into the solution, 3.42 of them are going to ionize, and the other 96, right, are not going to ionize. They're going to stay in the form of HA. So I basically make 4 and 96, or 3 and 97, if you do it that way. Okay, so degree of ionization is very small. It only ionizes a little bit. Good. All right, so that's page 17. That's calculating the Ka given the pH. And the key to it is the pH meter gives you the equilibrium concentration of hydronium, and that allows you to go through all of the calculations. You didn't need any X's in this question. Right? You didn't need any X's because you had an equilibrium number. We're going to use X's when we don't have the equilibrium number and we're trying to figure it out. Okay, so going in the opposite order, this is called calculations with Ka. So this time, you know the Ka value, and you want to calculate what the pH is. So here's an example. What is the concentration of nicotinic acid, hydrogen ion, and nicotinate, which is the counter ion, the A minus, at 25 degrees? Okay. Uh, I'm sorry. What are the concentrations of nicotinic acid, hydrogen ion, and nicotinate ion in a solution of 0.1 molar nicotinic acid at 25 degrees? What is the pH and the degree of ionization? Okay, so in this case, Ka for nicotinic acid is known. So it's given to you in the question, and I wrote it right here. The Ka is 1.5 times 10 to the minus fifth. We actually calculated that in the last question. Okay, let me cover up some of the answers here so you don't get confused. So let's do that. So we have our ice table over here. All right. So in this case, we write out the reaction. Again, HA plus water goes to H3O plus, hydronium ion, and the counter ion A minus. Okay, how much of this do I have in the beginning? I have 0.1. I have 0.1 because they told me that in the question. That's the original initial amount that was put into the solution. How much water do I have? So much, who cares, right? It's 55 molar. It's not going to come up in the calculation. You can leave it out or you can put an approximate sign like I just did, right? Doesn't matter. How much H3O plus do I have? Essentially 0 because the reaction didn't start yet. How much A minus do I have? The counter ion? 0. Nothing happened yet. Okay, once this stuff hits the water, it starts to react. Some of it goes over to the right, right? As it goes over to the right, the amount of it that reacts, we're going to call X. So this guy's going to go down by X. Look at the stoichiometry. This is a 1 to 1 to 1 situation. So if this goes down by X, this guy's going up by X, and this guy's also going up by X. They're in a 1 to 1 relationship. This is going to be some number that's huge and we don't care about it, minus X. But who cares? None of those things are coming up. Right? So another way to do this is fill this whole column out or just leave it out because it's not going to be in the Ka expression anyway. All right, we're ready to go. What's 0.1 minus X? 0.1 minus X. What's 0 plus X? X. 0 plus X is X. So those are my three numbers. This one we don't care about, right? We got a big number and we're going to take off X. It's still going to be a big number that we don't care about. Okay, so that's what happened here. Okay, so go back and look at this. When you get to this step, if you start to plug these three things into the equilibrium constant expression, I can do that. The Ka is always equal to the hydronium ion concentration times the counter-ion concentration divided by oop, the concentration of the acid that's left over at equilibrium that doesn't ionize, so that's HA. Okay. Okay, but guys, our Ka, right? Our Ka is a very small number. This stuff is a very weak acid. It's 1.45 times 10 to the minus fifth. So if this is 10 to the minus fifth, and this is 10 to the minus first, that's 4 orders of magnitude bigger. That's 10,000 times bigger. Whenever you're subtracting a number from another number that's going to be around 10,000 times bigger, this is going to be insignificant. It's like saying I have $10,000. Does it matter if I give somebody $1 or I don't give them $1? No. Next to my $10,000, it's not important. If I only had $7 and I go to give somebody or lend someone $1, that makes a difference because now I'm down to 6, right? But $10,000 minus $1, who the heck cares? It's the same as $10,000. So here, you're going to make an approximation. This is a case because this is so much bigger than this. It's okay to make the approximation. You're comparing the Ka to the original concentration of the acid. 10,000 times bigger, bam, no brainer, make the approximation. So here, I'm going to say that zero point 0.1 minus x is going to be so close to 0.1 that I'm just going to put 0.1 in there. And that makes Ka then equal to x times x divided by 0.1. And that's very easy math. I know my Ka was given to me in the beginning of the question. It's 1.45 times 10 to the minus fifth. Okay. All right. So that being said, let's solve for x. So this is going to come up here. Everybody agree? I'm going to get x squared is going to be 1.45 times 10 to the minus fifth times 0.1. So I just brought this up here. And the last step, I'm not interested in x squared, I want x. So x, I'm just going to take the square root of those two things. So I need the square root of 1.45 times 10 to the minus fifth times 1.0, excuse me, 0.10. So this whole thing is 1.45 times 10 to the minus 6. So I need the square root of that number. Okay. Okay, so this calculator, I think you do the square root after. So I'll do that for you. Okay, so let's put the number in. 1.45, right? Let me see my E button, EXP. Okay, 1.45, I hit the XP button. Put the lamp on here, maybe you can see a little better. Good. 1.45, and I need minus 6. Everybody see why I need minus 6? Because this times this is going to give me 10 to the minus 6. So I did that math already. Then I just need to take the square root of that thing. And that's my answer. And you see it's a very small answer, and I'll put in scientific notation. So x is equal to 1.204, right? So I'll leave that 1.2, 1.20. It doesn't round up to 1.21 yet, times 10 to the minus 3 moles per liter. Okay, what is X? Well, one of the things X is hydronium ion concentration, so that's how we're going to get pH, right? Go back up to here, line that stuff all up, right? What is X? X is the hydronium ion concentration. Okay, so the hydronium ion concentration is 1.2 times 10 to the minus fifth. I don't even have to write a molarity because you know anything in brackets is the concentration at equilibrium, okay, in moles per liter. What's the nicotinate? the counter ion, it was also X. Go back up to here. We defined X, right, as the A minus, the nicotinate, right? The nicotinic acid after it loses its proton is also X. So that's the same number. 1.2 times 10 to the minus 3. Okay. The degree of ionization. Let's do that. The degree of ionization is the A minus divided by the original amount of HA that they gave you, right? This guy was 0.1. Remember, right from the question, 0.1. Make that a little bit darker, right? Divided by the A minus. So this is going to be 1.20. This dividing by 0.1 is the same thing as multiplying by 10 times 10 to the minus 2. Okay, somebody wanted that in percent. This guy would ionize to 1.20%. Right, so how did I get from here to here? I just multiplied this by 100. That's what got it into percent. Okay, let's take a look. Then I only have one more thing to do. Okay, so we all agreed. We got this guy. We got this guy. We got the degree of ionization, right? Oh, the percent ionization is the degree of ionization times 100, 1.2. The degree of ionization was 1.2 times 10 to the minus 2. That's what I had here, right? If I want to write that as a number, I just have to move this decimal place back 2 times 1, 2, and that's my 0.12. So I got that. And then the last thing is, how much HA is left in solution? Well, that, even with the approximation, I now have a good estimate of what it was, and I can do the subtraction back. Okay, so that's the last thing. I'll just get a different piece of paper. So remember, go back up to here. Right, we dropped the X over here, but now that we know what X is, let's put it back. So we have 0.1 minus our 1.2 times 10 to the minus 2, and we're going to see that's a small number, right? That's going to come out to, I'll do it, 0.1 minus 0. Let's get over here. Minus 0.12, and we get 0.088. Let's see if we agree with that. 0.0988. So I must have made a mistake back here. Let me go back to here. So 0.1 minus 0.012. Sorry. 0.1 minus 0.012. I got 088. I'm supposed to get 098. What am I? Oh, duh. Guys, this is 10 to the minus 3, right? This guy's 10 to the minus 3. So when I do that subtraction, I have to I have to be subtracting x. What I was subtracting was this number, right? So it's not 10 to the minus 2, it's 10 to the minus 3. So one more time, sorry about that. Right? So 0.1 minus 1.2 e minus 3. Okay, so that's the right answer, 0.0988. Okay, so that's the HA. All right, I'll let you guys take a look at the rest of that. I don't want to go into any more detail. All right, that was way too much. Okay, so that takes care of page 18 of the notes. All right, so we did two examples. One in which I gave you the pH of the solution and you had to calculate Ka, and this one where I gave you the Ka and you had to calculate the pH. So last step, just going back and looking at that, I didn't do that. From the HA, you can always get the pH by doing what? You just need to take the log of this number. It's going to come out negative and you throw away the negative sign. So the log of 1.2 times 10 to the minus 3 is going to come out to negative 2.92. And then pH is minus the log of something, so it's going to change the sign back to positive. So your pHs will always be positive. There's not going to be any cases where you guys see negative pHs. Okay, it is possible if you have an extremely acidic solution that the pH can go below 0, but you're not going to see that. Good. Okay, take a break there. We have two more topics, polyprotic acids, and then we'll do the equilibrium for bases, which is very similar to acids, and I'll pick up there next time.